All right, matrix algebra, kids, and this is, you know, it's like the movies. We're all batteries.
Are you talking about The Matrix?
Yes.
You know, they may not have seen that. That's actually kind of an old movie now.
You know, maybe we should start class with a matrix clip every day.
I don't think that's a good idea.
Okay. Maybe.
So we're talking about matrices. Matrices is the plural of matrix.
Right.
And they look kind of like this. They are rectangles. And typically they have brackets. This should actually be like a bracket around it. It's not very clear.
No, but it's okay.
Okay, there's brackets around it, and then it's filled with just numbers in rows and columns. And it's important that you know which way are the rows and which way are the columns. So like this is row 1, this is row 2, and so on. And
I don't think it's almost next to impossible to tell you how important you understand the difference between the rows and columns in the order, because everything that we do with the matrix is related to the row, then the column. Right.
So the order here matters. Everything you do, you're going to do the rows first, then the columns. And so what I usually do is I usually think about it whenever I'm starting a problem, because I forget which way is which too. So when I think about it, I think columns like on a building, right? Are
like
up
Supreme
and down.
Court building or the state capitol or something like that.
Right. So these are columns up and down, just like on a building. And then once you know which ones are the columns, then you know the other ones have to be rows. They got to be rows. So each of these we can represent with like A to a subscript, and the subscript is the first number is the row that it's in, the second number is the column.
Right.
The other thing we can do is we can talk about the order of this matrix, which is the size of it in like a dimensional sort of way.
Or you could even say the shape.
The shape of it,
you know.
Right? And so you would say how many rows it has by how many columns it has.
Right.
So let's try an example here.
Let's do it.
Determine the order of the following matrices. So on this first one, we say how many rows there are.
Right.
There are 3. And then how many columns there are.
3.
So 3 by 3.
And
then,
that's not a multiplication.
No, it's
that just
not.
represents a dimension, like you would say, I have a box that's 3 by 4 by 4.
Yeah, exactly. On this one, there are 4 rows, so 4, and there are 2 columns, so 2. Here we have 2 rows.
And then 3 columns.
3 columns. That's pretty easy.
Right.
Just identifying the order. And then in the first matrix above, so by that I mean this one, identify element A subscript 12. So that means row 1, column 12.
Yep, column 2.
Oh, yeah, that's what I meant. Column 2. The first number is the row, the second number is the column. So
might be a handy thing for this lesson, maybe for several matrix lessons actually, to have some multicolored highlighters where you can see through, or pins. Because what you can do is you can actually highlight the row and the column, and where they overlap is the specific thing that we're interested in.
Right. So here is the first row, the second column. Where they overlap is the element A1, 2. So the answer to this is 2. Because that's what's in that spot.
There you go.
We've got some operations for matrices. We're allowed to add them, and we're allowed to multiply by a scalar, kind of like when we talk about vectors.
And we can subtract.
Technically, when we subtract, we're adding something that we multiplied by a negative. So yes, we can subtract, but really we're adding the negative.
So we're subtracting.
Kind of.
Well, to get to what Mrs. Stevenson is saying, all subtraction is adding the negative number.
Right.
So
we want to take these matrices and do A plus B. Matrix addition is super easy. You take the elements that go together and you add them together. So like first row, first column, plus first row, first column. So that
and this is where the highlight issue can come into play.
Yeah, you could potentially like highlight this a color, this a color, this a color, this a color, and then do the same thing over here so you can tell the difference.
Right.
So 2 plus 1 is 3. You can go either direction now. From here, I'll go down. -1 plus -2 is -3.
And notice that the things that she adds stays in the same place.
Right.
So row 1, column 1, plus row 1, column 1 goes in
row 1, column 1. 3 plus a -3 is 0. 5 plus a -4 is 1.
Boom.
That's A plus B.
Blamity blim blam. Dunskies.
So how about A minus B?
You're going to do the exact same thing, except now you're going to have negatives.
So I'm going to write
addition part
out what we're doing here. 2, -1, 3, 5. And we're subtracting. So I'm going to add instead, and I'm going to go ahead and change these all to negative of what they were.
Right.
So -1, +2, +3, +4. So by putting the negative inside, I would change this to addition, and now I can easily figure out what those are. 2 plus a -1 is 1. -1 plus 2 is 1. 3 plus 3 is 6. 5 plus 4 is 9.
There you go. So it became an addition problem, even though, that's what I was giving Mrs. Stevenson a hard time about just a minute ago.
3A.
3A just simply, easy for you to say, simply means multiply each element inside the matrix by a scalar of 3.
Right. It's like a more complicated distributive property thing. We're distributing the 3 into everything that's inside of here.
Everything.
So 3 times 2 is 6. 3 times -1 is -3. 3 times 3 is 9. 3 times 5 is 15.
There you go.
And last, 2A minus 3B.
So now you're going to multiply by the scalars first on both matrices, and then whatever you get, you're going to add.
Right.
And remember, we're going to take care of that negative sign by multiplying by -3. So we're good to go.
So 2 times the matrix A, so that'll give us 2 times 2 is 4, 2 times -1 is -2, 2 times 3 is 6, 2 times 5 is 10, plus, now I'm going to distribute the -3 into the second set of parentheses, so that's -3, +6, +9, +12. You watching to make sure I'm doing it right?
I started to daydream. Sorry, I have a soccer match later, and but I'm going to go with yes. It looks -3, +9, -6. Thanks for calling me out in front of everybody.
You're welcome. Okay, now let's add these together. It's not what my intention was. You really looked like you were actually hardcore paying attention.
Sorry, there's a soccer match later.
Excuses. Yeah. Hey, did you guys win last night?
We did. Yeah, it's pretty good. Yeah, Laramie Hall went nuts again. It was great. Good. Yeah, and she just got on the internet.
Yay! Awesome. All right, that's how you do matrix addition and scalar multiplication.
Don't let this be hard. This is not a hard thing.
Now, here, let's throw this out there. You can multiply any matrix by a number. That's fine.
Right.
But you can only add or subtract them if they have the exact same shape.
Right.
So all of these, well, they were the same matrix all the time. These were both 2x2 matrices.
So they have to go with 2x2 matrices.
Yeah, if you had like a 2x2 and a 2x3, you'd have to say, no, sorry, I can't do that.
Right.
And
like it's not possible.
Sense. There's not enough things to add together.
Right.
All right, now we're going to do some matrix multiplication.
Definitely have a highlighter maybe as you go through this one. I think it'll help a little bit.
This is tricky to keep track of.
Yes.
So we're going to use matrix multiplication to find AB and BA. So this is the case where these are going to be different. Whenever we normally multiply numbers together, like 5 times 3, that's the same as 3 times 5.
Right.
That's called being commutative. Matrix multiplication does not have that property.
No, it does not.
So
which makes it a little bit more difficult because you think that it does.
Yeah. So to do A times B, how even to explain this? This is
you're going to take the first row, the elements of the first row, and you're going to multiply each individual element of the first row with the first column of the other matrix. And then you're going to add those little pieces up.
All right.
So this is the first step. Looks exactly like what Mrs. Stevenson has written.
Right. So we take that's backwards. We take the first row and the first column, and what that finds us is where they overlap. That's going to find us element 1, 1.
Which means that we're going to be in row 1, column 1 when we get done.
So what we do is we do 2 times 1 plus 3 times -2. Which is
2 plus 2 minus 6.
-4.
So -4 goes into row 1, column 1. All right.
Okay. So now let's do the next thing. So we do now the first row and the second column.
Right.
Where those overlap, which is the element in the top right corner.
Right.
That's where we're going to put that answer. So 2
So row
times,
1, column 2.
Yeah. 2,
and you multiply each individual element.
So first, 2 and negative 3 plus 3 and negative 4. So that's negative 6.
Minus 12.
Minus 12.
Negative 18.
And
so
that goes
row
to the
1,
top right.
column 2.
New color. All right, now we're going to do the second row. So second row.
Second row.
First column.
First column.
So you're going to do negative 1 times 1 plus 5 times negative 2. So negative 1 minus 10.
Negative 9.
Negative 11.
That's what I said?
Yep. Totally.
Totally what I said. I don't know how you messed it up.
Row 2 and column 2. So that gives us negative 1 times negative 3 plus 5 times negative 4.
Right. And there's some patterns that occur here as well that you can see. Maybe a little bit easier if we had actually written these into the spots of the matrix where they were going.
Oh, you know, that would have probably been...
Well, go ahead and write it down right now. This is what you should get when you multiply A and B. So, okay, Steve, write in blue what you have written in blue right here. Put that in row 1, column 1. Big matrix style now.
2 times 1.
Write it exactly like that. Don't write the equals part. Yep. And then underneath that, and next to that is red. So red would be over here in this one.
2 times negative 3 plus 3 times negative 4.
Then purple in the lower left-hand corner.
Negative 1 times 1 plus 5 times negative 2.
And then green in the lower right-hand corner.
Negative 1 times negative 3 plus 5 times negative 4.
Okay, now notice there's some things that occur here. If you look in all of these by column, okay, notice that you have all 1s and all negative 2s.
Right. And
okay.
then
you have all negative 3s and all negative 4s. And then on the other side of that, if you'll look, you'll have the actual first matrix represented. So see the 2, 3, negative 1, 5?
Yeah, 2, 3, negative 1, 5.
Okay.
And then 2, 3, negative 1, 5.
There you go.
Again over here.
Yes. And so that's kind of another pattern that you can look for when you're multiplying the matrix.
Right. Now, for me to do B times A, I almost have to like write them in the other order personally.
Yes, you need to, or you'll make a mistake.
What happens is we're switching which rows and which columns we're dealing with. And for whatever reason, it doesn't really work so well whenever I try to do it personally in my head. So for BA, we've got first row, first column. So that's 1 times 2 plus negative 3 times negative 1.
Can we show them the pattern for this first one then?
So then here we should have
negative 2 times 2.
Negative 2 times 2 because this is the bottom left here, and then the 2's match up.
Plus
and then,
negative 4 times negative 1.
Right. Because the second number is the same in the columns.
Right.
And then the first number comes from what is the first matrix that we have, which is B.
And if you don't see that right away, that's okay. Write it out like Casey did on the first
right.
answer.
So let's start this here. Negative 2, negative 4, and 3, 5.
Negative 2, negative 4, negative... No.
No, just kidding. I want...
No. 1, negative 3.
1 negative... This is terrible.
1, negative 3, 3, 5.
1, negative 3...
3, 5.
3, 5.
Yeah.
Okay.
See, it's tricky. You got to pay attention.
1 times 3.
Yep.
Plus negative 3
times 5. And then we can fill in the rest of the pattern there. So it's going to be negative 2 times 3 plus negative 4 times 5.
And then we just have to actually figure out what all these are.
Yeah.
So this is 2 plus 4, which is 6. 3 minus 15,
negative 12.
Negative 4 plus 4, which is 0. Negative 6 minus 20, which is negative 26.
And you can have 0 in a matrix. That doesn't mess anything up. 0 is a number.
Yeah.
So it's okay to have in there.
Okay.
All right, good talk.
Next thing we're going to talk about is inverse matrices. And so an inverse matrix, it has all these cool things that it can do, and we'll talk about one of the cool things in the next lesson, but right now we're just concerned about what is an inverse, how do we find it, and this one property here, two matrices are inverses of each other if when you multiply them together, either direction, A times B and B times A, either way you get this thing called the identity matrix.
And the identity matrix is actually really cool because all it is ones and zeros.
Right. And so what happens is you have ones in a diagonal going from top left to bottom right. So if we wanted a 3x3 identity matrix, it has to be square.
It's got to be square. If it's not square, can't do it.
Then you have ones in the diagonal and zeros everywhere else. So this would be the identity matrix for a 3x3 matrix. And by the way, we didn't mention earlier, but a square matrix is a matrix where it is a square. Like, what does that even mean to have a square? It means the
same
rows
width,
and columns are
height.
the same.
Yep.
So if somebody asks you, hey, is that a square matrix? Now you can...
Now you can tell them. You can be like, hey, this is what a square matrix is, guys.
All right, so let's do A times B. Get our multiplication practice on. We're trying to prove these are inverses, so that's our steps, is A times B, see what we get. It should be the identity, and then B times A, see what we get. So this row, this column. So that's
3, 1
times 1
negative 2
plus negative 2
times 1
times 1. Okay. Row, column. So that'll be the spot here. 3 times 2 plus
negative 2 times 3.
Times 3.
And then you can fill in the pattern, or you could do rows, columns, whatever is most comfortable for you.
Absolutely.
And by the way, these take just a little bit of time. Please do not rush through these. Please do not try and save paper on these. Just
do it.
Just do it. Take your time, relax, write it all out. You'll be a better person, a better human being.
So when we work this out, 3 times 1 plus negative 2 times 1 is 1. 3 times 2 plus negative 2 times 3, that's 6 minus 6, which is 0. Negative 1 plus 1 is 0, and then this is negative 2 plus 3, which is 1. That is the identity matrix.
That's the identity matrix.
Let's see if we can do this the other way around now.
And if we can do it the other way around, life will be good.
1 times 3 plus
that's my cord. I left your cord in there. I didn't know if you needed it.
That's this row and this column.
Sorry, I looked up. I didn't see where you were
3.
at.
Sorry, this is negative 1 right there. 2 times negative 1. And then
1, 2.
This row, this column.
I'm thinking maybe you should have written these out again.
Maybe I should have, but it's too late now.
It's all over but the crying. Well, we can fill in the pattern here. This is definitely a fill in the pattern part.
Okay, so we have 1, 2, 1, 3.
So
1, 3.
Yep.
And then 3.
And then
negative 1. And then we've got 1, 2.
1, 3.
1, 3.
And then negative 2. There we go. Then we're not all cluttered up there. And 1. Okay, there we go.
Okay, this gives us 1.
3 minus 2 is 1.
This gives us 0.
2 minus 2 is 0.
This gives us 0.
0.
This gives us 1.
Boom. So those are inverses.
Yes.
All right.
We proved it. All right, now finding an inverse for yourself, we do this formula right here. And we represent an inverse by putting a negative 1 out by matrix. That exponent means inverse, just like it always has.
It doesn't necessarily mean to the negative 1 power, though. Not with a matrix. It's not a matrix to the negative 1 power. It's an inverse on the matrix.
Okay. So,
because if you put a number to a negative 1 power, you're saying 1 over that.
Well, that doesn't even make sense to put 1 over a matrix.
Right, that's what I'm saying.
Okay.
Yeah.
Okay, then I'm with you. So we do 1 over AD minus BC, and this is something we're about to talk about called the determinant, actually. It's these diagonals subtracted. So that's 6 times 1 minus 2 times 3. And I might have put that in the wrong order, but that's what matters is the first column, or the first diagonal is first, the second one second. And then this is a tricky part. You put D, which is 1, negative B, so that switches to negative, negative C, so that switches to negative, and then A. So what happens is you're switching the diagonal, and you make the other
negative
way negative. So this is 6 minus 6. Oh no, that gives us a 0 on the bottom. What that means, see how it says find it if it has one or state it does not exist? This is does not exist. If it did exist, we would have gotten something like 1/3.
Or -2.
Or something, and we would have had to distribute it into our matrix.
Right.
But this one does not exist.
D&E.
Let's find some determinants.
Let's do.
This is like a special thing again, kind of like the inverse. It's a special thing that you use all the time when you're working with matrices.
Right.
And
they're kind of cool.
Note, if the determinant of a matrix is 0, then the matrix does not have an inverse. That's
right.
what we just
found happen. That.
If it's a 2x2 matrix, then you are taking the diagonals and multiplying them together with a subtraction sign in between. A times D minus B times C.
Right.
So it's pretty easy to do that. So 3 times 2 minus 4 times 1.
And when you find determinant, you're getting a single specific number.
Yes. So earlier I pointed out that there were really brackets around the matrix. When you see like straight lines, that is actually telling you to take the determinant of the matrix.
Right. So when you're doing your homework with matrices and you write just straight lines like that, then you're telling us we're finding a determinant, which means that could be wrong if we're talking about a matrix.
Right.
So
be careful.
Yeah.
Now, when it's a 3x3 matrix, we don't have a handy box. It gets complicated.
It can get complicated.
We use this thing called cofactors.
Yeah.
And so what you do is you pick...
It's like that Facebook status. It's complicated.
Yeah, I guess so. You pick a row.
Yes.
So if you have a row that has zeros, that's a good idea to pick one. So I'm going to pick this row.
Are we finding the determinant or finding an inverse?
We're finding the determinant.
Okay.
So I'm doing cofactors.
Oh, cofactors. Okay.
So you put the first element, -1. And so what you do is you think about what the matrix is that doesn't include the row or the column that has that.
So you're actually going to work with the matrix 2, -1, -1, 3.
Exactly. I'm going to get rid of those or they'll get in the way. So 2, -1, -1, 3. Then you change the sign of whatever this is. So actually this should be a minus sign. So although it doesn't matter because it's 0. So minus 0 times, and then we'd eliminate those two.
Right.
That go with 0. So 1, 2, -1, 3. And then you go back to an addition sign, which this is a +1, so that works out, and then we write the matrix that has those eliminated.
Which is going to be the 1, 2, 2, -1.
Right. And now what we do is we take the determinants of these matrices that we came up with, which we know is the diagonal subtracted. Right. So -1, this will be 2 times 3 minus -1 times -1.
The middle guy is going to all be 0 because 0 times anything. Yeah.
Right. So there will be like a +0 in the middle. And then here we have 1 times -1 plus 2 times 2. So 6 minus 1.
Sorry about that.
Is 5. Still don't need that 0. This is 1 times
-1.
-1 plus 4, which is 3. Right? -1 plus 4?
Yep.
3. And so that gives us -5 plus 3, which is -2.
Now, there's another way to find this determinant, Mrs. K. Steve. Did you know?
I did know, and that's normally the way that I teach it, but this is
That's
shorter.
pretty fun, though.
That's shorter, especially if you have zeros.
Yeah, if you have a 0, for sure.
So the other way to do it is you I rewrite the first 2 columns.
That's what I do.
Okay.
It's like we have genius minds that are linked.
Right. And then you take the diagonals going... Do I have a highlighter option?
You know, try it out and see what it does. Chisel top, marker.
Let's try this.
Take the ones going that way. Oh, yes. Look at you.
You take these diagonals and you multiply them together. So you would do 1 times -1 times 1 plus 2 times 3 times -1 plus -1 times 2 times 0.
Oh, we love zeros.
Then you're going to subtract the ones going the other direction.
The other direction. So all of that minus the next row here. Who knew we had a... Highlighter? Who knew all this time we had a highlighter?
I think this is the main time that it's helped. -1, -1, -1, plus...
0, 3, 1.
3, 1, plus...
1, 2, 2.
1, 2.
And again, anytime you have a 0 in that matrix, finding the determinant just gets a lot easier because those things go away. But you're going to end up with the same thing. So
this is -7 minus, this is
-1.
That's
plus 4.
So that's 3.
-7 minus 3. Did you do your math right on top?
I don't know.
-6. Did you do your math right on bottom?
That's a great question.
Because that says -10, and the bottom says -2. So do we have an oops?
Probably.
Okay, so we're going to pause this and figure out where we have an oops, and we'll come back to you in just 1 second.
You guys probably knew this the whole time. I didn't subtract here. I did 1 times -1, and I had a plus sign, but it's -2 times 2. So that should be -1 minus 4, which
is -5.
Yeah, which is -5, which gives us -10.
There we go.
Now we match. So pick which way you like better.
Yeah, and they're both pros and cons both ways. Just whatever way you feel most comfortable.
Absolutely.